all, thank you for coming to listen to my talk. And this is not my first time to come to Vignan University. This is my second visit. 5 years back, I came to Vignan and I was so impressed with the infrastructure and various activities that are happening in this university. So I have returned back and it is my pleasure to come back. My name, as Professor has introduced, is Kolla. I am a faculty in Bowling Green State University. I have been teaching there over 30 years, and our department name is Electronics and Computer Engineering Technology. The Bowling Green is in state of Ohio. So if anybody is interested in contacting me, that's my email, skolla@bgsu.edu. First, let me talk a bit about the Fulbright program, under which I came to India 5 years back and spent, I believe, 3 days or so I was at Vignan. So the program, as Professor Srinivas has informed, is a binational program through which faculty and students also come from US to universities in India and various other countries also, and from India a group of faculty go to US to spend anywhere from a semester to a year, and during that period they will be associated with other universities to do research, and they can also come and teach. And it's an excellent program, but it is a very competitive program. Every year there will be requests to submit proposals. Once these proposals are reviewed and approved, every year I believe from India about 40 to 50 faculty go there, and I encourage the faculty from Vignan and other universities to apply and take this opportunity, and it's an excellent opportunity. Now, in this program, I came to IISc Bangalore in 2017, and when we come, we just don't stay in one place. We go to other universities and give guest lectures, and in that regard, I contacted Professor Srinivas and came here and gave a couple of guest lectures, and I am very impressed in this rural setting. You have an institute of this caliber, and the vision of the director that has established this university, and many of you are joining this university is an asset, and I encourage all of you to take various opportunities that exist in this university and progress further is what I would like to emphasize. And just like I came back from 5 years to here now to associate with all of you is a indication that there is a lot of good work going on in this university. Now getting back to my talk, is just going to be some basic ideas on research my students have been doing. It integrates latest artificial intelligence techniques and how they are applied to some of the electrical engineering areas, in particular electrical power systems, and in the power systems, protection is the area where we have been doing some work. The outline of my presentation is some introduction, and now within the power systems, microgrid is evolving, and a lot of research is going on in this microgrids area. Faults and protective relaying, some basics I will present. I will also give some basics about machine learning techniques, in particular neural networks, and deep learning techniques are the most common things that are coming up these days, and long short-term memory is one of the deep learning methods that I'm going to just briefly introduce, and apply these machine learning techniques to microgrid fault detection. both the ANN and LSTM methods. So we applied, and there are some results that we got, and conclude the topic with some summary of it. Can all of you hear me well? Yes, sir. Think so. Okay. First of all, we know in the power industry, one of the main challenges is blackouts, and here is some of the recent and blackouts that occurred all over the world, of which one of the significant blackout that occurred is in India in 2012. It's a very major blackout. 620 million people got affected. Similarly, one of the major blackouts that occurred in US is in 2003 time. So it just gives the importance of why protective relays and protecting electric power grid is very important, because once there is a blackout, as you can see, many people get affected. Now, what do we do to protect again, to take care of these blackouts? Is protective relays are used to monitor power system apparatus and disconnect in case of faults. Traditionally, these protective relays used to be built using electromechanical devices, and then solid state protective devices came into existence, and even solid state protective relays were more or less outdated. Microprocessor based relays are the latest technology, and it has been going on for 20-30 years, that research in the microprocessor based relays area. And within that, the logic part that associated with the microprocessor based relays is now being explored with machine learning techniques. They started with those simple neural networks, and now the deep learning techniques are being applied to this. Now all these machine learning concepts, they have evolved due to this smart grid technology that has come into existence probably some 15 years back or so. And smart grid concepts came into existence because of these three situations or conditions. First, expansion of the grid to accommodate renewable sources, particularly wind, solar, and various other renewables are being integrated into the grid. Then atomize and penetration of information technology into the traditional electric grid is the other tenet that they have considered, and development of new applications. These are the three things that are driving the modernization of the electric grid, which we call it as the smart grid. And what are the various things that can be accomplished is self-healing from power disturbances. That's one of the things that is associated with the blackouts. There are several other things. I don't want to go through reading these, but that's smart grid concepts is what is driving the research in the electrical area, of which with the renewable energy sources penetration, microgrid concepts have come into picture. So according to US Department of Energy, DOE, the microgrid is defined as a group of interconnected loads and distributed energy resources. So those are the emphasis is the renewables that are distributed energy resources with clearly defined electric boundaries that act as the main thing is it is can work as a single controllable entity with respect to grid, and it can operate either in grid connected mode or in islanded mode. The grid connected is just like a part of another source in the big grid, but it can work by itself in islanded mode. So the operation of these microgrids in both these modes is one of the challenges that gave rise to opportunities to work in the protection side. So integrating distributed energy sources presents technical challenges for controller protection. Protection methods used for conventional grid may not work for microgrid. The reasons being, when the microgrid is working in islanded mode, the fault currents are very low because the renewables are integrated into the grid through power electronic converters. So those power electronic converters have limited current capabilities. The next is at the distribution level, the current or the power flow used to be unidirectional with radial lines, but with the integration of renewables, there is a bidirectional current flows in the microgrid feeder. So both these challenges, they pose significant issues with the protection. So various approaches are used, and one possible approach is to use machine learning techniques to use in the microgrid protection area. This is pretty basic. What are the various different types of faults in general a transmission line or a microgrid line connecting can experience? I'm sure most of you are familiar with this. A three-phase power line may experience single phase to ground faults. There can be three different conditions like that, depending on which of the three phases is connected to ground. Two-phase faults, two-phase to ground faults, and three-phase faults. Okay? The traditional relays are overcurrent, and you can also use distance relays. So overcurrent relays, they basically detect the current magnitude. Based on the current magnitude, there is a set time. They use the current time characteristics to protect it, and distance relays, they measure the impedance, and based on the impedance they estimate the distance to a fault, and if the fault is within the protected zone, they disconnect. As I mentioned, these relays used to be implemented using electromechanical and solid state devices. The latest technology is microprocessor based relays. So here is a block diagram of the microprocessor based relay, which is pretty basic. Most of you probably are familiar from the power system. You need to access the voltages and currents. So we have transducers called CTs and TTs, which bring the analog signals of the power system into the relay, so that the analog input. Once the analog signals are brought in, you digitize, and digital data go into the microprocessor, and microprocessor implements several algorithms and logic, and if there is a fault, it sends an output to the digital output line to disconnect the faulted parts. So that's the basic microprocessor relay block diagram. Now some introduction to machine learning techniques. Machine learning is a vast area, and it is used in all sorts of electrical engineering, communications, and computer science, and various areas, correct? The basic things I'm going to touch upon are neural networks and some deep learning techniques, which I will just touch upon the long short-term memory. That's what we have worked in our research. The neural networks, probably most of you are familiar, it tries to mimic the biological brain neural network function into a mathematical model. An optimization technique allows the neural network to learn the rules for solving the problems by processing a set of examples. So it is like a pattern recognition type of applications. So that's the cell body which is being emulated in this single neuron, where we have inputs coming in with x1 to xn, these inputs are weighted with weights W1 to Wn, and they are summed. So that's the weighted inputs are summed, and there could also be a bias, and this whole weighted sum with a bias is sent through a nonlinear activation functions, and it gives you the output. So the output is the nonlinear function with the weighted inputs. Now the weights are the most important terms that tries to map the input to the output relationship. That is accomplished by selecting appropriate weights. The nonlinear function that used as the activator functions, there are many different ones, but the sigmoid function is the most common function. Now these single neurons are they do not have enough capability, so they put many neurons in neural networks. So ANN is a collection of simple processing units mutually interconnected with weights assigned to the connections. There are several types of neural networks. One is the feed forward, radial basis, and various others. And feed forward layer neural networks were extensively used in research in various areas. And here is the structure of the feed forward neural network structure. So each of these circles is the neuron that I showed you before. So they are connected in various layers, and each layer feeds into the other layer. So that's why it's called the feed forward layered neural network. Okay. Now each of these are the connections with some connecting weights. So the weights of single neuron has now become more populated. So the training of mapping with the input to the output have more freedom to select the weights. The training is the process where you select these W's that match the output to the input. The way the training goes about is they start with some random weights for the selected inputs and what output it should be. So with the initial set weights they compute the output, and if that output matches the target, then the weights are the proper weights. If not, the optimization process adjusts these weights till the time the inputs match with the target output. So that's how the weighting where the training goes about finding the weights. And there are again various different techniques available for the training, and most popular is the back propagation is the most popularly used training. Again, probably this is all very basic for all of you. If it is basic, I can skip over. But the extension of the simple neural networks is recurrent neural networks, where you have internal recurring connections that are occurring. So that recurrence gives you more freedom to again match the output to the inputs. An expanded view of the recurrent network is with time is expanded and shown in that fashion. We have again the number of weights have increased. The recurrent neural network is kind of a start of the deep learning techniques. So these lead to the very basic deep learning method is LSTM, which is called the long short term memory, where the simple unit that we saw in the ANN is now expanded into a much bigger unit. It has several types of gates. One is called the forget gate, and various other gates are there. There is a forget gate, there is input gate, there is output gate, there is a cell unit. Mathematically, an LSTM is expressed by such a complex mathematical equation compared to the simple neural network. So now you have many parameters to play with it. and also it gives some unwanted things are forgotten, and various other features are included into it. Okay, so that's the some overview of machine learning techniques. The other machine learning technique that is extensively used is the convolution neural networks, and we have not done any work, but the convolution neural networks is extensively applied. So now we try to bridge both the protection side and the machine learning side. So for that we have taken a microgrid. The data that is needed for this microgrid is simulated using a MATLAB based software which is SimScape. We have taken a IEEE 13 bus model, and to that IEEE 13 bus distribution line we have added renewable energy sources and created the microgrid. The sources that are added are, there is a wind generator, there is a solar, and we also put a fuel cell, so that's a solar. And when the microgrid is working in islanded mode, it to provide the necessary power that is being supplied by the main grid, we also have a diesel generator to support when it is working in the islanded mode. So these are the various different distributed generators connected, and that's the model that we have taken from the microgrid. Okay. It's a modified IEEE 13 node system. It's a 4.16 kV system, and the renewables that we added are the 250 kV solar PV, 1.5 megawatts wind with DFIZ as the generator, and we have the diesel which gives a 3.125 MVA, and a very small fuel cell which is giving very little power. Total load on this is 1175 kilowatts of the resistive and 389 kVAR. The microgrid is simulated in MATLAB SimScape. Different faults are simulated on one of the distribution line, and as you can see, this is no longer a radial line. You have various different sources are feeding into from various different sides. Okay. And that line is a 1,000 feet line. It connects the buses 671 and 680. So when we expand the actual SimScape simulation diagram is this one for that. So here is the solar, wind, and various other sources are connected to it. We created faults, all sorts of 10 faults that I described before. The voltage and current signals for the single phase to ground fault in grid connected mode and in islanded mode are shown here. And after one cycle, a single phase to ground fault is created, and you can see the voltages have oscillations, and the current magnitude in the faulted phase has increased. So this is the grid connected mode. Now the important thing to note is the fault current level in the islanded mode is much smaller than the grid connected mode. So if there is a relay that is operating and it is supposed to work for both modes at the same time, the relay settings that are set for for the grid connected mode will no longer recognize such small currents and detect them as faults. I am showing only the phase to ground faults, but we have done this simulations for all sorts of faults. And as I explained, fault currents in grid connected mode is almost 5 times that of the islanded mode. So with that simulation data, we want to detect all sorts of faults in both the conditions. The first is we did the work with the ANN. The structure of that protective relay logic takes the three-phase currents and three-phase voltages, and it identifies if there is a fault, what type of fault it is, and if there is no fault, it will indicate the no fault and it will not trip those lines. Now, in the case of neural networks approach, the inputs to the neural network are three-phase RMS currents. RMS currents is what we used. So from the sample data, we have to use some kind of a signal processing method to get the fundamental frequency RMS values of three-phase currents and voltages. And there are various different techniques to get those fundamental frequency components, and the most popularly used technique is discrete Fourier transform. DFT is what they use, and we have also used the full cycle DFT to get the RMS values from the sample values. And we collect the data, and we need to first select a structure for the neural network and then train it. And the structure that we selected and it worked well for the application is a two hidden layers and one input layer and one output layer neural network model is what has trained well. So two hidden layers with 10 neurons in the first hidden layer and 6 neurons in the second hidden layer is the one that trained well. These are the for single phase to ground fault. These are the voltages and currents, RMS values. That's the pre-fault. All the three voltages and currents are same, but once the fault has occurred, the faulted phase voltage has dropped. The faulted phase current has increased. And the trained neural network was able to detect by giving a 0 if there is no fault. The first cycle it has no faults, and then once there is a fault, it indicated there is a fault. So here are the three-phase voltages and currents, and the expected output for that particular fault. If there is a fault, it should go to 1, and it was 1. And we can see the faulted phase voltage has this is the no fault condition. If there is a fault, then the faulted phase for single phase to ground fault, the voltage has dropped and current has significantly increased in that faulted phase. We can see. So that's the data of testing of the neural network based relay, and this is for the islanded mode. In the case of islanded mode, after the fault voltages have dropped, but fault current has increased. The amount of fault current is much lower than the grid connected mode. And again, the neural network was able to identify the fault condition and no fault condition. So here is the three-phase voltages and currents for all sorts of faults, and it was able to recognize the no fault, single phase, phase to phase to ground, and three-phase faults when such condition data is presented to it. Okay, before I go to the LSTM, do you have any questions? I can pause and then I can come back.
What is the accuracy of
Now, what is the accuracy of its fault finding?
Fault finding.
Fault finding.
It's when we get to the LSTM, I will show you the accuracy of that. But for the ANN, we had an accuracy of 97% almost.
Okay.
It was able to identify the fault, 97%. For the cases that are not trained. For the trained cases, if we test, it's 100%.
Okay. Okay, sir.
How many test cases are there?
I have not shown that the test cases that were taken for the ANN were, I believe some 1000 test cases were there. For each line, we have created the fault set to 10%, 20%, 30%, 40% distances, and all 10 types of faults at each distance was created, and we used that at various different loading conditions and at various different fault resistances, and all. We have taken several cases.
How much minimum voltage underarm we have added
In the phases for the dead short circuit, the voltage has almost dropped to 5% of the actual voltage, and in that case, the fault resistance was also very low. Fault resistance was there. The most difficult thing is not the low fault voltage resistance, but high impedance faults are some of the difficult ones to detect, and it did quite well with the high impedance faults also.
Sir, sometimes we use artificial neural network. Sometimes people will go for fuzzy logic.
Correct.
Sometimes combination of neural networks and fuzzy logic. So selection of this method for analysis of faults or whatever it may be. Is there any method, is there any mechanism to identify the appropriate method for this?
What is good for what? That is itself is a research area to identify. To my knowledge, there is not a very well established method exists to find which combination of these methods are good. To my knowledge, I do not think there is a very well established method yet. Not only different methods, even within the neural network itself, there is still quite a bit of randomness. For example, how many hidden layers that we need, how many neurons that we need in each layer for the particular, not necessarily fault condition. If we are predicting load, even in any of these things, very well established methods, I believe it is still a research area. It is still evolving to the extent I know. That falls in computer science side of the machine learning.
I have one more doubt. What is the false alarm? How much is because it's to do with the smart grids.
Correct.
The moment you say
there is a fault.
There is a fault, but it's a false prediction by the ANN.
Oh, okay. So that's why.
That's where it all will collapse. Correct. Basically, it's
correct.
So how much is the probability of that? Because if you want to implement such thing,
correct,
it should be 100% foolproof.
Correct.
Otherwise, it's always.
So that's why what they do is they do not pick the lines with in the fault identification. Just with one sample itself.
Okay.
They take an average of few samples. Again, we should not keep waiting for a long time, otherwise the system will collapse. So they will see a succession of at least 5 to 6 consecutive ones. Then only they go for tripping. In that case, the accuracy is again about 90 to 95%, 90 to 19. 99 to 99.5% accuracy is there when they take those precautions.
Okay.
And in the LSTM, I am going to share with you how we did some accuracy analysis and all those things. It can give you a little bit more.
Okay. Do you need any? Basically, it's to replace the human intervention, correct?
Is not human intervention. It is to replace the. Human intervention replaces already occurred with the microprocessor based relays and all. The logic that existed before is being replaced with the machine learning.
No, but what is the difference? Basically, the microprocessor also by the logic which we built,
Correct.
the same thing it works already. So
Works already means not really. With the microgrids and all, when there is islanded and grid connected mode, those logics are not functioning properly.
Okay.
But with the traditional things, I think it is quite accurate now with the traditional microprocessor based relays.
Yeah.
With the microgrids coming into picture, again the research is evolving.
Okay.
The challenges exist now.
Okay.
Particularly the grid connected and islanded mode is one, and the bidirectional flows of the current flow, which used to be just a radial lines. So they are requiring these machine learning type of methods to be.
No, basically it's also a computer program. Basically, microcontrol is also a program which you designed with your logic.
Correct.
Again, the neural networks also is a computer program. Again, based on our logic, only our.
Correct. But the machine learning, they self-learn. So
There is a large difference.
correct. So that is a set algorithm that is put, but this algorithm, the machine learn and they adjust based on the conditions. So I think that's how it goes. Yeah. So there is some amount of that self-correction and self-healing exists with this machine learning. It's like a machine learning a car, driving a car. So with the smart machine learning kind of techniques, it can correct itself, and so now we can.
Basically, you are combining the feedback because I did this thing also on that. Basically, the weights which you mentioned,
Correct.
It's a computer program. Again, you are correcting the feedback.
Again, corrected by feedback.
Until you reach a convergence of that, you train it and then you sample testing. You are testing that, and you are saying that 98% or whatever it you decide.
Correct.
So basically, it's again a feedback system and reinforcing the thing. It's a computer program. I don't see as if it is a human being's mind is replaced there or something.
No, yeah, that can never happen. The human beings, my mind cannot happen, but we can get as closer, not as, we will never be able to get as closer, but closer to that situation where it's not just a set algorithm, but that algorithm can correct itself.
Just based on feedback.
It can correct
the real-time inputs, and again it
feeds back. Correct.
Self-learning.
Self-learning is there. That's what it is.
Okay.
Yes. Okay, so now, any other questions or?
Students, please. Sir, how much data you use for training and how much data you
Okay. The data for training we used in a transmission in a distribution line. We have created false at 10%, 20%, 30%, 40%, 50% like that. So there is 10 different sets, but we used that for training. For the testing, we have created false at 75%, 85%, 95%. So we had about 30% of the cases that were not used for the training, and the rest was used for the training. And it was able to identify all the means about 99% of the time it was able to identify the conditions that were not used in the training. Okay. For the LSTM, I have given the some basics of LSTM. Again, the main difference between AN and LSTM is there are more parameters that it can correct, and it can self-correct itself. But the structures also become very involved with the deep learning models. The process is similar to the neural network. You have to select the inputs and select the structure of the LSTM, like whether how many hidden layers are needed and how many neurons in each layer, kind of concepts like ANN. We also need to select the LSTM structure. You need to train the LSTM the same way and test the LSTM with appropriate data. So this is the basic structure. So now, one thing we tried via LSTM that was not done in ANN is, in the ANN we have extracted the RMS values using discrete Fourier transform, and some others used the wavelet transforms and other transformation methods are used to extract features, and they use those features to train the network. But here with LSTM, with so much of power it has, we try to use the instantaneous voltages and currents directly instead of starting with the DFTs and all those things. This is the structure where we have three-phase instantaneous voltages, not the RMS values, and three-phase instantaneous current goes with the LSTM, and we can identify a little bit more elaborately all the faults in this case. We are AG, BZ and all those. So, but even the other one also can do that. So the way the training went here is so here is the three-phase instantaneous voltage and currents. We took a window of instantaneous values and fed as the inputs. We have various different windows we tried. So these windows, however many samples that we have in this window, and that window is shifted, and that's the data that went in. So movement of the data window, so win1 is it has completely pre-fault data, so the fault is created here, and you have win5 and all, they are completely post-fault data, and in between while it is transitioning, then you have some transitional data also. So there is no issue of anything happening pre-fault, and there is no issue with anything happening, it is fully post-fault. But in this transition, when the transition is taking place, so you have some fault and some non-fault data, so that's where the things get a little trickier to train. Okay, so here is the data that some of you have asked. So this is the amount of data we used. The pre-fault data samples used are 76 samples. It corresponds to one cycle. And the post-fault data samples comprised of 259 samples, which corresponds to 3.6 cycles of data. And it gives a total of 335 data samples for 4.65 cycles, and the increment where the data is moving is by one sample. So this is the actual structure. So it takes the three-phase instantaneous voltage and current. You select the data window, and it needs a sequence layer, LSTM hidden layers, fully connected layer, softmax layer, and classifier layer. So these the LSTM structures itself get a little bit more involved than the simple ANN. But it is expected with the existing computational power that we have. This level of complexity is not a issue of implementation anymore. Even if it is, it's going to go away. So then we train and we test, and finally it does identify the faults. That's what is expected. Now the various different softmax and various layers that we have selected are there are hidden units are 350, hidden units are layer 2 are 200, and there are 3 hidden layers. So those are the amount of units that they have, and we use the Adam optimizer, and we basically use the MATLAB for deep learning toolbox is what we have adapted to do this. Yeah, so these are correspond to that. So this is the training process, the MATLAB training of the relaying scheme that we have. It shows the accuracy and loss functions. Now the data windows, we tried various different. One is a 1/12 window, 1/8 window, and 1/4 window. That's the maximum we used. Whereas the ANN, discrete Fourier transform, we used the full cycle. So it takes full cycle to identify, more than full cycle to identify. But here you can identify, if we are successful, we can identify within 1/12 of cycle, or as high as 1/4 of cycle. So we were successful, but of which 1/8 window is looked very promising, so that's what we settled on. 1/8 window of the data is what So to answer some of your questions, these are the various parameters that we looked into to see how well it is recognizing accuracy, precision, recall, and FN score. So these are TP is the true positives. It correctly identified its true negatives, correctly identified negatives, and false positive, false negative. So these are the various indices that we use to quantify the effectiveness. Okay. So here is a data for 1 pulse cycle window, 1/8 cycle window, 1/4 cycle window. The accuracy for the no fault, the no fault itself is 100% accurate always, and there are everything is above 99 points. The lowest we got is 99.77 is the accuracy, and even these most of the time corresponded to the window when the window is transitioning from no fault to post fault. There is a transition period is where some of the issues have come, but still it's a very high accuracy. Again, the same thing showed as a confusion matrix. There were 13,600 no fault cases, and it was able to identify all of them correctly. The single phase to ground faults, there are 5,163 it identified correctly, but 14 of them out of 5,000 were disclassified. And so it gives how many are misclassified, and the accuracy or classification accuracy is so varies from 99.77 to 99.94. So this is the testing performance where the previous one is the training, how well it trained, and this is the testing with the untrained data, and even for that the accuracies are very high. The testing performance evaluation is tested with untrained data for faults at 45% of the distance, and the accuracy was 99.93. Again, it's a confusion matrix, and here it is showing us the no fault to single phase to ground fault is identified properly, and there's a no fault. So for the phase B to ground fault, see, once it is fully in the fault, there is no problem. So this, in the transition, it has identified some of those are misidentified. So those are the ones that are contributing to the slightly, that the 99.7 whatever it is the result of those misclassifications. Anyway, so we did this for both grid connected mode. So these are the grid connected mode results, and we did this for the islanded mode also. So both are there. One is the grid connected mode, and other one is the islanded mode. This is the islanded mode results. Here you can see in little bit more clearly the three-phase voltages and currents and its identification. For a single phase to ground fault, easy fault that occurred, so those are the voltages and currents, and it was able to identify accurately. The slightly some issues have occurred here where the fault is a AB fault. It has in the transition there are some misclassifications. So in this case, again during the transition there were some misclassifications there, and in this particular case the misclassifications occurred even after the fault data is fully populated with the fault. It's not only in the transition. So that's one case it was contributed to slightly more inaccuracy. So those are the results of the LSTM. So in summary, the LSTM model can detect and classify microgrid faults using only instantaneous voltage and currents, and we do not need additional signal processing like DFT discrete wave transforms and others. The LSTM model can identify various microgrid faults for both modes of operation, that's the grid connected and islanded mode. The model can detect the fault and classify faults for 1/4, 1/8 and 1/12 cycle windows. Yeah. So application of machine learning techniques to microgrid protection is what we looked. Both ANN and deep learning is what we have looked. These techniques at this stage we have tested with the simulated fault, but we really need further research and field testing. This way the product developments, and we have to actually build these relays and first do the test in a lab setup, and then we need to go into the real-time implementations is what needs to occur. I myself did not do most of the work. My graduate students are what have contributed. The ANN work we have presented at a IEEE Green Tech conference with my student Peter Onawanga, and just in May we have presented the LSTM one with another student. It's at IEEE conference we have presented these results. So there are a few other the importance of fault protection for microgrids. This Sardam paper is a good paper where it identifies the grid connected and islanded and then bidirectional flows and various things what found there. The Swizer is probably even here we use the microprocessor Swizer relays, and they are doing quite a bit of actual implementations in the in their developmental facilities, and also they are coming up with the real relays that can work with the microgrid. That Swizer is a well established relaying relays company. So before I conclude, I would like to express my gratitude to Fulbright Fellowship Program that brought me to Vignan few years back, and it also motivated me to come back and be associated with all of you. And I'm very impressed actually from 5 years back to now. The research productivity has so significantly increased in these 5 years, and I wish the progress continues, and to this work my graduate students have contributed. So graduate students that have contributed some of the work, and Peter and Hossein are the students, and some of the material that I presented, some of the graphics of the relays and all are borrowed from the internet, so some credit goes to whoever created those things, so I don't take the complete credit. So thank you for patiently listening to me.